Hello everyone, my name is Guangxu, and I'm happy to be here to present our recent work, collaboratively improving topic discovery and word embeddings by coordinating global and local contexts. First, let me introduce some background knowledge. A text corpus usually contains two types of context information, global context and local context. The global context information of a text corpus typically refers to the document level word co-occurrence information, in other words, the words in the same document. And the local context information of a text corpus refers to its word level neighborhood information. In other words, the neighborhood words of a focus word within a context window. And the document level global context information of a text corpus carries topical information, which can be utilized by topic models such as LDA and PLSA to discover topic structures from the text corpus. And those topic models usually follow the bag of word assumption and assume that each topic is composed of a mixture of latent topics, and each latent topic is a multinomial distribution over words. For example, given a document about art and donation, let's have a look at LDA's perspective on this document. As we can see that from LDA's perspective, this document is composed of 4 different topics: arts, budgets, children, and education. And also the topic structures and topic words and the weight of each word can also be learned by LDA in the form of multinomial distributions. As we can see from this table, words belonging to the same topic are listed in the same column. And in contrast to the global context information, which carries topical information, the word-level local context information of a text corpus contains semantic and syntactic information. Word embedding models such as the neural probabilistic language model and skip-RAM, they have been proven able to capture the semantic and syntactic information in the text corpus. Those word embedding models usually follow the distributional hypothesis that words occurring in similar contexts tend to have similar semantic and syntactic properties. This is an example of how the local context information can characterize the semantic property of a word. For example, fill in the blank according to your personal judgment. The cat is blank on the carpet. And now we have the local context information. We need a focus word. Possible answers are the cat is sitting on the carpet, or the cat is standing on the carpet. The cat is running on the carpet. The cat is sleeping on the carpet. And of course, many more other words with similar properties. As we can see that given this neighborhood word information, no matter what your personal judgment is, it has to be a word with similar properties. It should be a verb in the present continuous tense. And these semantic and syntactic properties of words can be captured in the vector space by word embedding models. This figure is an example of the 2-dimensional projection of the word embeddings about capital cities and countries learned by work2vec. As we can see from this figure that words are projected to specific locations based on their semantic properties. In this example, the country vectors are on the left and the capital cities are on the right. And the capital cities are parallel with their corresponding countries. So now we know that the global context information carries topical patterns, and these topical patterns can be utilized by topic models to learn topic structures from the text corpus. And while the local context information of a text corpus carries semantic properties, and these semantic properties can be utilized by the word embedding models to learn word embeddings from the text corpus, then our motivation is, since we know both types of context information contain useful information and they are complementary to each other, why don't we exploit them collaboratively? Then maybe we can learn better word embeddings and topic structures. Let's have a look at some related works. In order to utilize both types of context information, the global context information and the local context information of a text corpus, most of the existing composite models combine topic models and word embedding models in a heuristic and a separate manner. They usually keep one of the model fixed and use the output of that model as the input, as the next step input to help the other model. One common way is to use pre-trained word embeddings to assist in topic discovery. For example, LFTM, latent feature topic modeling, and Gaussian LDA. They first learn word embeddings from a large external corpus such as Wikipedia, and then they replace the multinomial distribution over words with a probability function defined in the word embedding space to generate word embeddings. And the other way to combine topic models and word embedding models is to use pre-trained topic structures to assist in learning word embeddings. For example, the topical word embedding, it uses pre-trained LDA topic structures and use this pre-trained topic structure to assist in learning word embeddings and topic embeddings. However, there are basically two challenges in combining topic discovery and word embeddings in this separate manner. The first challenge is the difference of semantics between the external knowledge base and the current dataset. A large external corpus such as LDA is usually used to learn pre-trained word embeddings or pre-trained topic structures. It is a safe choice since Wikipedia contains a lot of context information, but it is not always the best choice because the semantic of Wikipedia might be different from your current dataset. And the second challenge is that external knowledge base is not always available. In some research domains, such as biomedicine, there's no such knowledge base as comprehensive as Wikipedia. So facing those challenges, we propose to simultaneously exploit the global and the local context information within the same corpus rather than using an external knowledge base. So then we can take advantage of both the idea of globality from topic models and the idea of locality from word embedding models. And then hopefully we can collaboratively improve topic discovery and word embeddings together. To do so, our proposed model follows three basic assumptions. The first assumption is about how to utilize the global context information. We assume that each document focuses on only a small number of topics, and each topic assigns high probability to only a small number of words. And our second assumption is about how to utilize the local context information. We assume that words appearing in similar local context tend to have similar syntactic and semantic properties and should be projected to nearby areas in the embedding space. And our third assumption is about the collaboration between the global and the local context information. We assume that words close to each other in the embedding space tend to have similar topic distributions and vice versa. And those aforementioned three assumptions correspond to three building blocks of our proposed model. So we'll introduce those 3 assumptions individually before we finally present our unified model. The first one is the global context assumption. We can realize this assumption by factorizing matrix D into 2 low-rank non-negative matrices, where matrix D is the global document word matrix, T is the topic word matrix, and theta is the document topic matrix. Both T and theta are non-negative matrices, and this non-negativity of T and theta ensures the interpretability of topic distributions. And the other terms here are the regularization terms to prevent overfitting. And for the local context information, we can factorize the local context matrix W into the product of matrix B and C, where W is the word co-occurrence matrix constructed from the local context information. And B is the word embedding matrix, and C is the context word embedding matrix. And our third assumption is responsible for the collaboration between the global context and the local context information. So by factorizing the topic word matrix T into the product of the topic embedding matrix A and context word embedding matrix C, we ensure that words close to each other in the embedding space should have similar topic distributions, and also words with similar distributions should also be projected to closed areas in the embedding space. And so finally, by unifying the 3 assumptions, we propose to utilize both types of context information jointly and to discover topic structures and learn word embeddings collaboratively via collective matrix factorization. So in this way, the topic structures learned by our model are not only sparse latent representations of documents learned from the global context information. Those topic structures also ensure that words close to each other in the embedding space to have similar topic distributions. And so similarly, the word embeddings learned by our model do not only account for the local context information that words appearing in similar local context in similar local context are projected to nearby areas in the embedding space. The embeddings learned by our model also take the topic distributions of each word and the global context information into consideration. So to do the parameter inference, we can first expand our objective function to vectors, as this equation shows, and then by iteratively setting the gradient to 0 with respect to each vector, we can obtain the following closed form updates for each vector. And then we repeat this procedure until it converges. And then we conduct experiments on 2 popular datasets in the text mining domain, the 20 News Group's dataset and the Reuters dataset. Since our model is able to simultaneously discover topic structures and word embeddings, we adopt several topic models and word embedding models as our baselines, including non-negative matrix factorization, PLSA, LDA, Gaussian LDA, LFTM, CBAL, skipgram, and etc. Here we show some quantitative evaluation results. The first one is for the topic structure evaluation. And we use the topic coherence score to measure this. The topic coherence score is an automated evaluation metric to measure the coherence of each topic. It follows the intuition that top words in the same topic frequently co-occur in documents. So according to this equation, we can see that the higher score means the more coherent topic structures. And these tables show that our model is able to discover more coherent topic structures with the help of both types of context information. And we also conduct a document classification task on the topic proportions learned by our model. Since for the traditional topic models, they only utilize the global context information. And our model is able to utilize both types of context information, the global context information and the local context information. And our model achieves better classification, precision, recall, and F1 scores. And the second experiment is for the word embedding evaluation. The word embeddings are evaluated by Spearman's rank correlation with human ratings. And the Spearman's rank correlation measures the consistency between the word embeddings and the human ratings on a set of word pairs. And the human ratings are collected via some crowdsourcing platforms. And this table shows that the word embeddings learned by our model are more consistent with human judgments. This is probably because that for most of the word embedding models, they require a lot of context information to learn good word embeddings. And that's mostly why Wikipedia is one of the most frequently used dataset to learn word embeddings. However, for such small dataset as the 20 News Group dataset we used in our experiment, it is crucial to utilize as much context information as possible to learn good embeddings because the amount of local context information is limited. So since our model can utilize the additional global context information in addition to the local context information, we can learn better word embeddings more consistent with human judgments compared with the conventional word embedding models. And here are two illustrative figures of the word embeddings and topic embeddings learned by our model. The first figure on the left is the two-dimensional projection of the word embeddings learned by our model. And we can see that the word embeddings learned by our model do not only show the semantic properties, which is carried by the local context information. They also show some topical patterns, which is carried by the global context information. And the second figure on the right is the two-dimensional projection of the topic embeddings learned by our model. And each topic embedding is annotated with the name of this embedding and top 5 words in this topic. And we can observe that the semantic similarities between different topics correlate with the distances between the corresponding topic embeddings. And this figure also shows an example of how the topic of Christian on the bottom right transitions to the topic of Middle East on the top left through the topics of Bible and religions. And in conclusions, we proposed a unified language model which is able to simultaneously exploit the global and the local context information. And the proposed model collaboratively discovers topic structures and learns word embeddings. And the topics and words are jointly trained and embedded in the vector space that preserves the semantic regularities, while sparse and interpretable document topic distributions are achieved at the same time. And finally, the experimental result validates the efficacy of our proposed model. Thank you.